think about this for a second. Not long ago, machine translation could give you some really funny, nonsensical
Oh,
results.
absolutely. Laughably bad sometimes.
Right. And now you've got AI that just translates conversations, websites, almost perfectly. It's seamless. What happened? What was that huge leap?
A really pivotal moment, I'd say, was a paper back in 2017. Attention is all you need.
Okay, catchy title.
Yeah, it introduced this totally new neural network design called the transformer. It came from a team, mostly at Google Brain, uh, Google Research, University of Toronto.
Hmm?
Names like Vaswani, Shazir, Uskarate, and others. A key moment.
Attention is all you need. So for you listening right now, maybe using AI tools, maybe just curious, why is this paper, this transformer thing, so important?
Well, because the transformer is basically the engine driving so many advanced AI applications you see today.
Like what?
Sophisticated language models, those really good translation chatbots.
Yeah.
A lot of them have transformer DNA in them. So understanding its core ideas gives you a real leg up in grasping modern AI.
All right.
And that's our mission today, really. We want to unpack what made the transformer special, why it was such a breakthrough, and look at its impact. And, do it without drowning you in super technical stuff.
Sounds good. So let's set the stage. Before the transformer arrived, what was the go-to method for tasks like machine translation? What were people using?
The dominant players were recurrent neural networks, RNNs. You probably heard of LSTMs or GRUs, gated recurrent units.
Yeah, I've heard of LSTMs. They process sequences, right? Like words in a sentence, one after another.
Exactly. They have this kind of internal memory trying to keep track of what came before as they process the sequence.
Which makes sense for language, word order matters, but what was the downside? What were the limitations?
The big one was that sequential processing itself, doing things one step at a time. It makes it inherently difficult to speed things up with parallel computing during training.
Ah, okay. Because each step depends on the previous one finishing.
Precisely. So for really long sentences or documents, it just became slow, a real computational bottleneck.
And people were already thinking about attention then, weren't they? The idea of focusing on important words.
Oh yeah, definitely. Attention mechanisms were around and they were improving things, but they were usually bolted onto these RNN structures. They weren't the core engine itself.
So attention was like an add-on feature, not the main principle.
Pretty much, yeah. It helped, but you still had that underlying sequential limitation of the RNN.
Were there any other attempts to break free from that one word at a time processing?
There were.
Yeah.
People experimented with convolutional neural networks, CNNs, for sequences.
CNNs, like they use for images.
Kind of, yeah, adapted for sequences. Models like Extended Neural GPU, ByteNet, ConvS2S. They tried to process things more in parallel.
And how did that work out?
It helped with parallelization, but they ran into a different problem. To connect words that were far apart in the sequence, the number of computational steps needed still grew with the distance, maybe linearly, maybe logarithmically, depending on the model.
So still a challenge for capturing those really long-range dependencies efficiently.
Exactly. It was hard to relate, say, the beginning of a long paragraph to the end effectively.
Okay, so we have RNNs, sequential, slow for long stuff. We have CNNs, more parallel, but struggle with distant connections. This really sets the scene for something new. Enter the transformer. What was a radical idea here?
The absolute core idea was simple but radical. Get rid of recurrence and convolutions entirely.
Entirely, wow.
Yep. The transformer relies solely on attention mechanisms, specifically self-attention, to draw these global connections between input and output words.
Just attention. What was the immediate payoff for that big change?
Two massive advantages jumped out. First, huge parallelization potential during training. Because it wasn't sequential, you could process all the words in the input sequence pretty much simultaneously.
Like looking at the whole sentence at once instead of word by word.
Kind of, yeah. Think multiple processors hitting different parts of the sequence at the same time. Much faster training. The second advantage was relating any two words, no matter how far apart. The number of operations needed to connect any two positions in the sequence became constant. O1 in complexity terms. Distance didn't matter for the path length of information flow.
Okay, that's a big deal. So relating the first word to the last word took the same basic computation path as relating two adjacent words.
Exactly. Now, structurally, it still used an encoder-decoder setup, which was familiar.
Right, the encoder processes the input, the decoder generates the output.
Yep, the encoder maps the input sentence into a sequence of representations, like numerical vectors. The decoder then takes those representations and generates the output sentence, one word at a time.
And it looks back at what it's already generated, right? That autoregressive property.
Correct. It uses its previous output to help predict the next word, like how you write or speak.
Okay. And inside this encoder and decoder, what are the main components? The building blocks.
They're both built from a stack of identical layers. The original paper used N to 6 layers for the base model.
6 layers in the encoder, 6 in the decoder.
Right. And each layer has a couple of main sublayers. In the encoder, it's a multi-head self-attention mechanism followed by a simple position-wise feed-forward network.
Okay, self-attention and a feed-forward bit. What about the decoder?
The decoder layer has those two, plus a third sublayer sandwiched in between. This third one is also a multi-head attention mechanism, but it pays attention to the output of the encoder.
Ah, so the decoder can look back at the encoded input sentence. Makes sense. Let's dive into that term, self-attention. What's the self part about?
Okay, first just attention in this context. Think of it like this. You have a query and a bunch of key value pairs. The attention mechanism calculates how much the query matches each key.
Like searching for something relevant?
Kind of. Then it takes the values associated with those keys and combines them. But it weights each value based on how well its key matched the query. So relevant values get higher weights.
Okay, a weighted sum of values based on query key similarity. Query keys values. Got it. So what makes it self-attention?
In self-attention, the queries, keys, and values all come from the same place, the output of the previous layer in the network.
So if we're processing a sentence, each word generates its own query, key, and value.
Exactly. And then each word's query is compared against every other word's key in that same sentence.
Ah, so every word is looking at every other word, including itself, to figure out context and relationships.
Precisely. It allows the model to directly weigh the influence of any word on any other word within the same sequence, regardless of distance. That's how it captures those long-range dependencies so well.
That makes intuitive sense. Okay, now what about multi-head attention? Sounds like doing this multiple times.
You got it. Instead of just calculating attention once with the full-sized queries, keys, and values, you first project them down into smaller dimensions. You do this multiple times, H times. The paper used H8, hates heads,
Great.
with different learned projection matrices.
8 parallel projections.
Then you run the attention mechanism, specifically scaled dot product attention, which is the core calculation, independently on each of these smaller projected versions in parallel.
So 8 mini attention calculations happening at once.
Yep. Then you concatenate the results from all 8 heads and run them through one final projection layer to get the output for that multi-head block.
Why do that? Why split it into multiple heads instead of one big attention calculation?
It allows the model to jointly attend to information from different representation subspaces at different positions. Think of it like looking at the relationships from multiple perspectives or angles simultaneously.
So one head might focus on, say, grammatical links, while another looks at semantic meaning.
That's the intuition, yeah. It prevents the model from just averaging everything out, which might happen with a single attention mechanism. It can capture different types of relationships in parallel, much richer.
Okay, that makes sense, richer connections. So how are these multi-head attention blocks actually used inside the transformer? You mentioned 3 ways.
Right. First, there's the attention mechanism within the decoder that looks back at the encoder's output. Here, the queries come from the decoder's previous layer, but the keys and values come from the final output of the entire encoder stack.
So the decoder is querying the encoded input sentence, saying, what part of the input is relevant for predicting the next output word?
Exactly. That's how the translation, for example, stays grounded in the original source sentence. It's similar in spirit to how attention was used with RNNs before.
Okay, decoder looking at encoder output. What's the second use?
That's the encoder self-attention. This happens within each layer of the encoder stack. Here, the queries, keys, and values all come from the output of the previous encoder layer.
So within the input processing, each word is looking at all the other input words to build up a richer understanding of the input sentence itself.
Precisely. It helps the encoder understand the internal structure and dependencies within the input. The paper has a nice visualization, figure 3, showing attention heads linking words like making to more difficult, even though they're far apart.
Right, capturing those long-distance grammatical links directly. Okay, and the third use?
That's the decoder self-attention. This happens within each layer of the decoder stack. Similar to the encoder, the queries, keys, and values all come from the previous decoder layer. But there's a crucial twist.
Ah, yes, the autoaggressive part. It can't look into the future.
Exactly. When generating the output sequence word by word, the decoder should only attend to words it has already generated. So in the decoder self-attention mechanism, they apply a mask.
A mask, what does that do?
It essentially blocks the connections to subsequent positions. It sets the attention scores for future words to negative infinity before the softmax step, meaning they get 0 weight. So each position in the decoder can only attend to positions up to and including itself.
Got it. So it enforces that left-to-right generation process. Clever. Okay. Besides attention, you mentioned position-wise feed-forward networks in each layer. What's their job?
These are actually pretty simple. After the attention stuff in each layer, both encoder and decoder, the output goes through this feed-forward network. It's applied independently to each position.
The same network applied to each word's representation.
The structure is identical, yes, but it's applied separately at each position. It usually consists of 2 linear transformations with a real U activation function in between. The paper used an input-output dimension of 512 D model and an inner dimension of 2048 E to FF.
So it's just adding some extra computational muscle at each position.
Basically, yeah. It helps process the information gathered by the attention mechanism further, allowing for more complex transformations before passing it to the next layer.
Okay. And how does the model actually deal with the words themselves, turning them into numbers and back?
It uses learned embeddings, just like many other NLP models. Input words, or tokens really, and output words are converted into vectors of a specific size. D model 512 again in the base model. Standard stuff. Pretty standard. Then at the very end of the decoder, there's a final linear layer and a softmax function. This turns the decoder's final output vector into probabilities over the entire vocabulary, predicting the most likely next word.
Right, predicting the next token.
An interesting detail is that they share the weight matrices between the input-output embedding layers and that final pre-softmax linear transformation. It saves parameters and seemed to work well. They also scaled the embeddings by the square root of D model.
Okay, sharing weights, scaling embeddings, efficiency tricks. Now, a crucial question. If you've gotten rid of recurrence and convolation, which naturally handle word order, how does the transformer know the position of words in the sequence? Self-attention itself seems position agnostic.
That's a fantastic point and absolutely critical. It needs that positional information injected somehow. This is done using positional encodings.
Positional encodings. Okay, what are they?
They're vectors that have the same dimension as the embeddings, D model. These vectors are simply added to the input embeddings at the bottom of both the encoder and decoder stacks.
So you add a position-specific signal to each word's meaning-based embedding.
Exactly. This vector encodes information about the word's position in the sequence. Think of it like adding a unique address tag.
And how are these address tags generated? Are they learned?
The paper actually proposed a fixed method using sine and cosine functions of different frequencies.
Sine and cosine waves, why?
The idea is that for any fixed offset k, the positional encoding for position pose plus k can be represented as a linear function of the encoding for position pose. They hypothesized this would make it easier for the model to learn to attend based on relative positions.
Ah, so the relationship between the encodings reflects the distance between the words.
That's the intuition. They did also experiment with learning the positional embeddings directly from data, like learning word embeddings.
Yeah, Dad. How did that compare?
They found it produced almost identical results in their experiments. But they chose the sinusoidal version because it might allow the model to generalize better to sequence lengths longer than any it saw during training, which is a potential advantage.
Interesting trade-off. Okay, so that's how order is handled. Stepping back, why is self-attention ultimately so effective compared to RNNs or CNNs? The paper had a table comparing them, right?
Yes, Table 1. It highlights a few key things. First, computational complexity per layer. Self-attention is roughly ON2D, where N is sequence length and D is representation dimension. RNNs are OND2.
So self-attention can actually be faster if the sequence length N is smaller than the dimension D, which was often the case in the models being used.
Right, especially with techniques to restrict self-attention for very long sequences. But the really big wins are in the next two comparisons.
Which are?
Minimum sequential operations. For self-attention, it's O1 constant time in terms of sequence path. It can process everything in parallel. For RNNs, it's ON, fundamentally sequential. CNNs are somewhere in between, maybe O log, with clever kernel setups.
That constant time for parallelization is huge for training speed.
Massive. And the third point is maximum path lengths for information to travel between any 2 points in the sequence. Again, for self-attention, it's O1. Direct connection.
Instantly connects any two words.
Yep. For RNNs, it's ONN. Information has to pass sequentially through all intermediate steps. For CNNs, it's often O log N. Shorter paths make it much easier for the model to learn long-range dependencies.
That really crystallizes the architectural advantages. Faster computation, potentially, massive parallelization, and direct long-range connections.
Exactly. And as a bonus, the paper suggested self-attention might lead to more interpretable models.
How so?
By visualizing those attention weights, seeing which words are paying attention to which other words, you can sometimes get insights into what the model is thinking. The appendix figures show attention heads seemingly learning things about syntax, like connecting pronouns to the nouns they refer to, anaphor resolution.
Like the model highlighting its own reasoning process. That's fascinating. Okay, theory sounds great, architecture's clever. How did it actually perform? What were the results?
The results were pretty stunning at the time, especially in machine translation, on the standard WMP 2014 benchmark for English to German translation.
A tough benchmark.
Very tough. The big transformer model set a new state-of-the-art BLEU score, beating even complex ensembles of previous best models. And it did so with significantly less training costs.
Better and cheaper, faster to train.
Yeah. The paper mentions the base model trained in just 12 hours on 8P100 GPUs, which was dramatically faster than previous state-of-the-art models. The big model took about 3.5 days. They saw similar state-of-the-art results on English to French translation, too. Table 2 really lays out these quality and cost improvements.
A massive leap, then. Did they test it on anything besides translation to see if it generalized?
They did. They applied it to English constituency parsing, figuring out the grammatical structure of sentences.
A very different kind of task, needs understanding of syntax trees.
Right. More structured output, often longer sequences. They used a 4-layer transformer, tuned it a bit for parsing. Even trained only on the standard Wall Street Journal dataset, a relatively small dataset for parsing.
What happened?
It performed surprisingly well. It outperformed most previous models, except for one highly specialized recurrent model, the recurrent neural network grammar. What was really striking was that it outperformed the classic Berkeley parser even when only trained on that limited WSJ data.
That's impressive because previous sequence-to-sequence models usually needed much more data to beat strong traditional parsers like that.
Exactly. It showed the transformer wasn't just a fluke for translation. It had a strong inherent ability to learn, structure, and generalize, even with less task-specific architecture tuning. Table 4 has the parsing details.
So it demonstrated real versatility across different kinds of sequence problems. Okay, let's try and wrap this up. If you had to boil down the core innovation, the absolute key takeaway from attention is all you need.
It's the radical shift from sequential processing, RNNs, or locally focused processing, CNNs, to relying entirely on parallelizable self-attention for sequence modeling. That's the revolution.
And that enabled better performance, much faster training, and crucially, a much better way to handle long-range dependencies.
Couldn't have said it better myself.
The aha moment for me is really internalizing how that self-attention lets every piece of information directly interact with every other piece, instantly bridging those long distances that crippled older models.
Yes, that direct path is key. And the impact, well, it's been immense, hasn't it? It completely reshaped NLP. Most of the large language models you hear about today, they build directly on the transformer architecture.
It became the foundation for so much that followed.
Absolutely. And its influence is spreading beyond just text into vision, audio, multimodal AI.
Which leads to that final thought, perhaps. If attention worked so incredibly well for language, where else can this fundamental idea of selectively focusing on relevant information take us? What happens when we apply these principles to even more complex data, like the paper hinted at? Images, video, scientific data.
That's the big open question, isn't it? Understanding this shift towards attention as a core mechanism really helps you frame how AI might continue to evolve and tackle increasingly complex problems in all sorts of domains. It's a powerful concept to grasp.
Definitely food for thought. If you, listening, want to go straight to the source, the paper is Attention is All You Need by Vaswani et al., presented at NIPS 2017. It's quite readable, actually.
And for the more technically inclined, the authors released the code 2 as part of the Tensor 2 Tensor library on GitHub, so you can really dig in if you want to.